So what we are discussing today is, let me start with some connection with what we did earlier. So we have PDFs which are known, but they are very difficult to sample from, right? Sometimes they could be difficult to evaluate, but in this part of the course, we are concerned with PDFs which are known and are possible to compute or easy to compute, but they are very difficult to sample from. Okay, let me write it in the title that we have PDFs. Okay, I think that are or you can say PDFs, you can say some P of X or P of Z, whatever, that are computable for a given X, but difficult to sample from. Right? So the question is, how do we obtain the samples? And the next question is, how do we use the samples? So what is our goal? Either to get the samples, right? Or to compute some statistics over these samples, which means some expected values over these samples, right? Let's say when you say X is sampled from PX, and the samples X sampled from PX are expected value over these samples. So, which we compute using Monte Carlo estimation, right? Sum over and where we are X is, and let's say your sample goes from 1 to capital S and you have 1 upon, right? This is simply Monte Carlo estimation. This you already know, right? Now the thing is, today we'll be seeing some more methods to do the same thing. But every method has its own requirements, its own conditions, its own pros and cons. So let's see today, we are going to discuss about rejection sampling. Okay, before we go into rejection sampling, one point about this, right? So we saw how many samples do we need to compute this particular thing? So the answer is generally 15 to 20 samples or even less are sufficient. So 15 to 20 samples are sufficient generally, but there could be a situation when those samples do not represent my original PDF properly. In other words, my samples are confined in certain region. Let's say I have a Gaussian mixture model, and if I get all my samples in this region, and maybe only a few samples from this region, because the number of samples is very small, so it could be possible that I may get, let's say, 1, 2, 3, 4, 5 samples, 6, 7, something. So which means because my number of samples is very small, so there could be such biases so that my effective sample size becomes very small, right? My effective sample size is very small in this case. Okay. So we'll discuss such cases in little more detail today. Okay, so let me start with our topic. It's called, first we are going to discuss rejection sampling. It's a very interesting concept. And a very clever concept. Before I go into explaining the algorithm or the concept, I would like to start with something very intuitive. Let's take this example. Imagine you have got a complicated, let's say, a PDF, right? This kind of a PDF. Maybe it's bound, the support is finite, which means it is non-zero only in a finite region. So this is my P of X, this is my X. So how will I sample from this PDF? So when you will sample from this PDF, you will basically, let's say it's a Gaussian or truncated Gaussian. Then you can compute these points. So my X is distributed as P of X, right? The random variable X has a PDF P of X. But now let's do something interesting. We construct a new, let's say, random variable, which is a tuple X comma Px. What is the distribution of this random variable or this random vector, you can say? What is the distribution of this random vector? Yes? So this is, I think, a very important observation. And whoever made this observation was able to further progress the work in this direction, the rejection sampling and so many algorithms which came up. So this was the key. This X comma Px, now if my X was one-dimensional, X comma Px is two-dimensional. It lies in this entire 2D space. What is the distribution here? It is uniform in this region. Basically, in this region, basically. Right? It is uniform in this region. So let's say if I have a 2D space, let's say I can make it bounded also, some bounded 2D space which contains Px. Now, if I randomly sample things from here, what is that? So me getting a point in this shaded region will be uniform. That means, or if I get a point here, let's say I randomly sample in this bounded box, let's say I do uniform sampling in this 2D space, then if my point what is the probability that it lies inside this curve? This is very simple. It's uniform, right? Because everything is uniform. Now,
sir, how is the distribution uniform?
How is the distribution uniform? Okay. Let's say I obtain a sample. Yeah, it's a good question. Let me try to explain it. Let's say if I sample from this distribution, I will get, okay, let's start with a discrete example. It's always good to start with some discrete example. Let's make something like this. Here my X is discrete. Okay, let's say probability of 0 is this value. Probability of 1 is this value. Probability of 2 is this value. Probability of 3 is this value. Okay, and everything else is 0. Now, how many times will I obtain 0? Like compare it to a histogram, right? How many times will I obtain 0? It will be the total number of zeros. The number of getting zeros will be approximately equal to some k times p of, let's say if I'm sampling capital S times, then it will be capital S times p of 0. Number of ones is equal to capital S times p of 1. Number of twos will be equal to capital S times p of 2, and similarly p of 3. Right? Do you agree with this?
Yes, sir.
If I am obtaining random samples, let's say I obtain 100 samples, then overall their distribution will be something like this, right? That makes sense, right? Because simply from our frequency rule, probability of 0 is number of zeros divided by total number of samples, right? So this is how it is, right? Now, if I consider, let's say, break this further into blocks. Right. So you will, within each block, you will get equal number of samples, right? Within each block, this I'm calling this as one block. Within each block, you will get almost equal number of samples, right? Because the number of zeros is, let's say, 3 or 30. Number of ones will be 1, 2, 3, 4, 5, 50. Number of twos will be 1, 2, 3, 4, 40. Number of threes will be 20, right? The number of samples will be more, right here. Are you getting it? 3, 4, 5, 6, 7, 8, 9, 10, 14. There are 14 blocks. Let us say equal to 140. Right? This means how many times 0 will appear here? So number of zeros will be approximately equal to 3 upon 14. That is the value 3 upon 14 times 140, or 140 into this, which is approximately 30. Right? Similarly, 140 into 5 upon 14, approximately 50. Right? So in this way. So within this area, they will be uniformly distributed. Do you agree with this?
Yes, sir.
Yeah. So that's what, and when you extend this to a continuous random variable, this was a discrete random variable. Let's say X was a discrete random variable. And the PMF is here. The P of X is the probability mass function. So here, similar analysis if you do to continuous case. So this is the thing that you get within this area, within this region. This is uniformly distributed. And yeah, that's it. That's the thing. Right. So this is a simple observation which makes the thing very powerful. And this is also true for a vector. My X could be a random vector, which means it could be a tuple of many random variables, right? And P of X is the joint distribution of all those random variables, or is the PDF of the random vector X. And
Sir?
Yes.
Sir, can you repeat the last thing when we said that they are uniform? Like I got it up to the calculations and the values after that.
Okay. Imagine that you're filling up this space.
Okay.
About 30 points here, about 50 points here, about 40 points here, 20 points here, right?
Okay.
So you can say they are like uniformly distributed within this region.
Okay. Okay.
So this is a kind of understanding which is at the core of rejection sampling. Okay. That if you take the tuple x comma px, then in this region, our points will be uniformly distributed. Okay. Now let's start with the theory of rejection sampling. Okay. So in rejection sampling, let's say you have a PDF P of X, which is difficult to sample. So what you do, so the goal is to sample from PX. Okay. Or it could also be, my PX could be either given to me or it could be in that form, if you remember from your Ising model, some P tilde X upon some normalizing constant, right? So this could also be where Z is basically intractable. So our goal is to sample from this distribution. So how we can do it is within rejection sampling framework or using the idea of rejection sampling. So what I will do is get a simpler distribution QZ or QX. Get a simpler distribution called QX, such that I will write down later, but let's first draw something. Let's say this is this is some PX, right? And you want to sample from this distribution. What can you do? You can construct a QZ, which is always bounding your QZ, means QX, which is always bounding your PX. Is this possible? Constructing a QX, which is always bounding your PX, which means QX is always greater than or equal to PX. Is it possible?
No.
Why?
Area will be greater than.
Yes, very good. So what I will do is I'll multiply this Q with some constant, let's say K. Now this is possible, right? K times QX. Right, this is possible. Okay, now my area is K. Instead of 1, now my area will be K, right? Okay, now what I do is I take a simpler distribution QX, which means it is simple to sample from. Here simpler means easy to sample. Okay, I have an QX which is easy to sample. Now if you can get samples from QX, can you do something to get samples from X? The idea is this. Get samples from Q. Actually, you want to get samples which lie only inside this blue curve, right? But you have samples uniformly spread all over the green curve. So what you have to do, you ignore or you reject all the samples which are outside this. Okay, which are outside. So these samples you reject. Right? These ones you reject. you have got samples in this area and you are rejecting them. So basically you have got samples from this space, which is x comma k times qx. No, sorry, in this 2D space basically. And in this uniform, you have, sorry, how do I say? You have samples which are uniformly distributed within this space. Actually, it need not be bounded. It could be continuous. So you have samples which are uniformly spread in this entire green region, but you want samples only within this blue region. So how will you do this? You will simply take your sample. You will take your sample KQ comma, take your sample x comma KQX, right? This is your sample. And then you say, if this lies, okay, let's say this is some sample. Let me call it as a random variable u. Right, this lies in this green bordered region. Now, if my x comma u lies in the green shaded region, the shaded green region, reject it, otherwise accept it. Right? Does that make sense? If it lies in the green shaded region, then reject it, otherwise accept it. And this sample, if it is accepted, it will be a valid sample from your PX. Accept it.
So to make this decision, we have to find the value of, we have to put a sample in P and Q, K into QX, and then subtract NC.
Repeat once again.
I mean, so we need to find the value of the sample being put in the P, the value of this, and the second value, K into Q of sample. How would we make this decision? So whether to reject it or numerically?
Very good question. Very good question. So now tell me how to sample x comma u. This is the question. How do you sample x comma u? In this basically green bordered region. The answer is yes, please. Anybody can tell?
Excuse me, sir.
Yes.
So if we can sample X, we sample X first from uniform whatever range that we have.
No.
The green.
How will you sample x?
So we can sample x from the simple distribution qx and then calculate the PDF of x.
Pardon, then you will calculate?
The corresponding, like the PDF of X corresponding to that green distribution
Yeah.
for the second point.
Yeah,
So
that
for
you
that-
compute. Okay. Then you will compute value of QX. Let's say I sample some X naught from QX. Okay. And I know the value of QX naught now. Right? Okay, then sample X naught, compute
yes,
QX
sir,
naught.
then just concatenate both these points, and I think that would give us the required data point that we want to sample.
But is it inside the green region or outside the, basically, is it in the green shaded region or in this white?
We could multiply the QX naught by K, the constant that we have
Okay.
chosen, and then
Okay, then you will,
give us-
let's say I got this as my X naught, right, from QX. And now I computed K times QX naught, it will be here. This is my K times QX naught. Then what will you do now?
So we would
Sa-
also have to find P of X naught. So
Okay, then you will compute P of X naught. Okay, let me do that. Then,
and then compare the two values, sir. K into Q of X naught and P of X naught, sir.
so K into Q of X naught will be always larger than P of X naught.
So we can sample a uniform variable whose bounds are between 0 and KQX naught.
Okay, yes, very good. So you are sampling U from uniform 0, comma, K times Q of X naught. Well, this is capital Q. Whatever is small. Okay, then what do I do then?
If that sampled value is greater than P of X naught, reject it, otherwise accept.
Very good. Very good. Thank you. So that's what we did. We first sampled.
So can you explain the last step, sir?
Okay, good. Good question. I mean, I will explain. We first sample X naught from Q of X. Now we are sure that this sample lies within this green bordered region, right? This is for sure. Now we have to find out whether it lies within the white region or in the green shaded region. So for that, what we do is we construct a uniform random variable. This is a uniform, like, inside this, everything is uniform, right? Inside this area, everything is uniform. Now we construct a uniform random variable U. So this is, U is uniform between 0 to KQX naught, basically on this line. On this line. Now my U lies certainly on this line. Now I can check whether my U lies inside this blue region or outside this blue region. If it is lying outside this blue region, then I reject it. If it lies inside, then I accept it. Right? And then you can say, if accepted, X naught is a valid sample from X. Otherwise, you repeat the step. Otherwise, go to step 1. This is step 1. So repeat the whole process. Does it make sense? Does that make sense? Okay.
Sir,
Yeah.
So basically, we already knew the blue PDF, right? We
Yeah.
just used the green PDF to generate samples, and we just rejected those who are not in the region of the blue PDF.
Yes, yes. We can compute the value of Px naught, but we cannot sample from Px naught because it's very complicated form.
Oh, yes. Sir. Okay.
So this is a very nice method.
Sir, how do we know, sir, how do we, I mean, calculate Q of X, that distribution?
Yeah, we'll have to know that value, right?
Yeah,
At that point.
we have to construct, we have to find out a distribution Qx such that k times Q of X is always greater than or equal to Px. We also have to decide k. So we have to, so you have to, this you have to decide, you have to find out for your problem, and this also you have to decide. You have to find
So,
a
sir,
key. You have to find
so,
a
sir,
key.
this is another problem that you have to solve. First, you have to
Yeah.
find
Yes.
optimally Q of X.
Yeah, could may not be optimal, but it should be valid.
So QX will be necessarily like Gaussian or something else also. Like here we are drawing the
It could be
Gaussian.
anything. It could be anything that is
Easy
simple.
to sample from.
Yes. Okay. Let's go to now. Okay. Here, one small simplification is possible. The simplification is I can sample my U uniform 0, 1, and if my U is greater than P of X naught on K times Q of X, then reject. It means it's the same thing. Just because you have readily a uniform sampler available between 0 to 1, I will just sample from there and then I will compare it with this number. Just a scaling thing, nothing special. Okay.
Excuse me, sir.
Yeah.
So in one of the earlier classes, you gave us a problem of uniformly sampling points from within a circle.
Yeah.
And then the solution was to sample points in a 1 cross 1 square and then reject all the samples that don't lie inside the circle. So can we use this formulation to solve? I feel that this is similar to what we did over there.
Yes. Yes. Very good. Yes. Exactly same. This rejection sampling, that is also rejection sampling. Both are same things.
So can you formulate that in a mathematical way? Because I don't understand how we fit in the circle constraint in this formulation.
I can do that, but the basic principle is this, that yeah, when you sample, I think I described that concept here. This is the basic concept, that x comma px is uniformly distributed in this shaded region. This tuple is uniformly distributed in this region. This is the crux of both the problems, whether you are using rejection sampling or you are using that method to estimate the value of pi, right?
Yes, sir.
Yeah, this is the basic principle.
Okay, sir. Thank you.
Thank you. Good question. Now we have to, yeah, let me just do the formality of writing it properly. So here you can say, instead of saying get, I can say choose. Choose a simpler distribution Qx such that Q of X is always greater than or equal to P of X K times Qx is given for some fixed K. This is a fixed K. And then I think all the steps I've already written. Then these steps are there basically. Number 1, sample X from Qx, or you can say X naught from Qx, and then sample a U from, or you can say U naught from, what is it called? uniform 0, 1. And then if my U naught is, you can say, greater than P of X naught on KQ X naught, then reject X naught, and otherwise accept X naught. That's it. That's it. This is the algorithm. Very simple algorithm, right? So first you have to choose a simpler distribution QX, which follows this property, and then sample. That's it. Okay, now what are the limitations of this method? Somebody can take a very stupid distribution, let's say uniform distribution, which is a very simple thing. Or let's say, yeah, but the problem with uniform is that it has a finite support, which means it is non-zero for only a finite range of, or a finite length of X, and it is 0 outside. So, and we can't have a Q which is 0, but P is not 0. That is not allowed. So uniform may not work if your PX has infinite support, right? So you may use a Gaussian curve, and you may take a very large K so that whatever distribution you have here, it lies within that, right? Which means a stupid solution, or a kind of, you can say, trivial normal 0, 1, and take a large K such that your basically any complicated distribution is there. It just take such a large K that your normal 0, 1 will anyways encapsulate it, right? So this is a very dumb approach. What is the drawback? What is the problem with this approach? So to see that, yeah,
Rejecting a lot of samples.
Becomes inefficient because a lot, like we have that shaded green region that becomes very large, and so a lot of the samples just go waste.
yes, very good, very good. You can visualize the thing that if this is very large, let's say if I have some distribution, let's say my P of X is something like this, then you have to raise this K very, very large. Even this is small, maybe really huge K you want. And you see an entire area is a waste, and all these samples you will be rejected. And you have uniform, right? So basically you'll be getting uniform in this entire region. So these many samples will be wasted. So if I ask you approximately how many samples will be wasted, so can you tell intuitively number of samples wasted? Or you can say fraction of samples wasted. Fraction of samples wasted is how much?
K minus 1 by K.
K minus 1 upon K. And if your K is very large, then approximately all the samples are wasted, right? Let's say my K is 100. 100 minus 99 upon 100. So 99% of the samples are wasted. Only 1% samples are used. It's a very computationally very inefficient, right? And therefore, this large K becomes inefficient. Therefore, you have to choose a Q as close as possible. Right? Because ultimately, what is your K? Because your K will be what? Your K is, you can say, is equal to the argmax of what? Argmax of Q upon P, right? No, not argmax, just max. It's the max of Q upon P for any X. Am I right? No, P upon Q. Right? So that my K times QX is larger than any PX, right? My K is the maximum of this. Okay, so these were just peripherals. I think the basic theory is this. Now I can, yeah.
So didn't we introduce K to make the area one? The objective when we the main objective of introducing K was to make that area under the PDF one, the QX PDF. So
Area under QX PDF 1, no. No. Area will not be 1, area will be K, no? This area is K, the green bordered region.
so how is it a valid PDF, sir?
It's not a valid PDF. We are never sampling from this PDF. We are sampling from, where is our algorithm? We are sampling from QX.
Okay, sir, got it.
It's only here that we need.
Yes, I got it.
Okay, thank you. Good questions. Now I will just do some mathematical derivation of what we intuitively solved here. Okay, now how many, what is the probability of accept? What is the probability of accept? This is equal to probability of accept given X naught into, I should write here, not PR, this is probability of accept. Let me write it as this. This is not P, but this is the general probability. What is the probability of accepting a sample? So probability of accepting a sample is probability of accepting given the sample X naught into probability of the sample X naught, right? And integration over all X naught, right? Right? And let's compute this. What is this probability of accepting given X naught? Yes. What is this value? What is the probability of accepting a sample X naught? This one, right? P of X naught upon K Q X naught. Right? Because this is a uniform thing, 0 to 1. And this is my P of X naught upon K Q X naught. This is my U. And if my U is lying above here, then I reject it. And if my U lies below, then I will accept it, right? So what is the probability of accepting? It is Px naught upon KQx naught, all right? Oops, my pen is not working very fast. Let me do something about it. I think now it should work faster. P of X naught upon K times QX naught. And what is the probability of X naught? This is
QX naught.
QX. Very good. Now, if you substitute these values, what do you get? This is equal to integration of this QX naught and QX naught get cancelled. You get P of X naught on K times D of X naught. This is equal to what? Yes?
1 by K.
So if your K is very large, then your probability of acceptance becomes very small. Right? That's why you don't want a very large K. That's why you choose a QX, which is as close as possible to PX, so that your K, which is max of P upon Q is very small, right? If they're almost same everywhere, then this is approximately 1. So K will be approximately 1. K can never be smaller than 1, right? Okay. So that's it. I think this was all about rejection sampling. Now we'll go to the next concept, which is called importance sampling. It's done. Now we go to the next concept, which is called importance sampling. If you have any questions, feel free to ask.
Excuse me, sir.
Yes.
So when Q is a PMF, so then Q of X naught would denote the probability of X naught, sir. When it is a PMF, but here it is a PDF, right?
Once again, tell me.
So when Q is a PMF, I mean discrete for discrete cases.
Yeah.
I mean I'm talking about the right thing. So then Q of X naught denotes the probability of finding X naught.
Yeah.
Right. So but in case of PDF it doesn't, sir.
Why?
It's proportional, but because it is unbounded, no sir. PDF is unbounded.
PDF is unbounded. PDF is unbounded. I didn't get it. Means what do you mean by?
I mean, sir, Q of X naught. When we put the value, find the value in a PDF, sir, it can be greater than 1, right?
Yeah. Yes.
So how is it probability of X naught equal to Q of X naught, sir?
If X naught is a random variable, continuous random variable, then no problem. Q of X naught can be greater than 1. What is the problem? Right. See, you are sampling X naught from QX naught, from QX. So probability of X naught will be equal to QX naught only, because you're sampling from that distribution. Right. There is no problem, even if X naught is a continuous variable, Q is more than 1, no problem. Right. Okay, now we go. There is one case left here, that what if my P of X naught is not known, but what I know is only P tilde X or P tilde. And so in that case, I will have to choose a QX which encapsulates P tilde X, and my K can be appropriately large, right? Basically, I will choose a QX which is greater than or equal to P tilde of X, because I don't know Z. So that Z will not play any role in this uniform sampling, right? Because I cannot compute that Z. But that's all right. There is no problem, because that Z is kind of absorbed in this constant K. So we don't have to worry about that in that sense. Right? Now let's come to the next topic, which is called importance sampling. So the problem is same as we had earlier, that we have a PX which is difficult to sample, but we can compute the value of PX easily. Right now, here the problem is little simpler. I don't want my goal is not to get samples from PX, but to compute some expected value on PX of some fx. I want to compute expected value of some f, some function f, where f is a function of a random variable x and x is sampled from PX, where PX is difficult to sample. But easy to compute. All right, that's our goal. Now my goal is not to get the samples, but only this. Right? I can still use rejection sampling here, right? I can use rejection sampling, and I can compute from the samples. I can compute this expectation, right? So rejection sampling is one solution. Let me write down the solutions which are available. That's a solution 1, rejection sampling, right? So from rejection sampling, you get the samples and then Monte Carlo to get the, so basically your expected value of F will be approximately equal to 1 upon total number of samples. S is equal to 1 to total number of samples. F X S, right? Where XS comes from rejection sampling, right? XS follows PX from rejection sampling. All right, this is one possible solution. Okay, let's look at some other solutions. Another solution is it is possible that my rejection sampling is very inefficient, or I'm not able to find some suitable QX in that region for that PX. So I may not be able to use rejection sampling, but still I can solve this problem. Let's look at the formula of EF. So my expected value of F in general, this is Fx, Ex, Bx integration, right? That's what it is in general. Now what I can do is I can sample X from a uniform distribution, right? And then I consider this whole thing as a function. So this is, let's say, expected value of X sampled from some uniform grid, right? And then Fx, Ex, right? Or in other words, this is equal to we don't need to take 1 upon S. Because this, because P of XS will be 1 upon S, right? So, oops. This thing will be equal to 1 upon S. This is from XS are points on a uniform grid. I will explain this in a moment. So let's say I give you a one-dimensional. Consider an example here. Consider an example here that you have got one-dimensional random variable. And I ask you, what is the mean of this PDF? I want to compute expected value of X. So what you can do is you break this down as a histogram or as into a grid. So what you do is, this is my X, right? So what I do is I will say this is equal to summation over, take this point X times PX. Let me call this XS, the points on the grid. Right. So using this, I have approximated my PDF to be a kind of histogram on a grid, right? And then I can compute these values and I will get the expectation. Does that make sense? Does that make sense? Yes. Okay. I'm assuming that you understand it. Okay. It's very simple. You just approximate your PDF as a PMF, and then on each grid point, you compute the value and add them up. That is the expectation value, right? You have made a grid to approximate it into a PMF. Okay. Now, what are the limitations of this method? Yes. Actually, this method is very powerful, and if you can do it, and with a sufficient bin size or grid, this spacing between the grid, you choose it sufficiently small, then very efficiently you can compute any of these expected values very easily. This is a very, very good method, but there are some limitations. What are the limitations? Yes. Am I audible?
Yeah. This is the limitation, right? Curse of dimensionality. If my X becomes multidimensional, then my grid also will become multidimensional. So a computational complexity will grow exponentially, right? The computational complexity will grow exponentially. That's the limitation. Okay. So now what do I do if my X is large dimensional? So I go for another solution. Solution number 3. Now this is importance sampling. So we do something similar. This idea converts my PDF. What did I do? I grouped these two terms, and then that made a kind of uniform PDF, right? And I sampled my X from a uniform PDF, and by grouping these two things together, right?
Sir, why are we not dividing the end result by S?
This term with S?
Yes.
Okay, good question. So what I have done, okay, what is happening behind the scene is, I will say this is divided by some capital S, multiply by some capital S, okay? Here, okay, let me say capital N, which is the grid size. Because all my points are coming from the grid, each point is coming once. So I will say my X is uniformly sampled from the grid, or basically it's like the uniform sampling, right? Now this is N times this is N times 1 upon N. So actually this is.
Yes.
Right. So that's why they got cancelled and it didn't appear. Okay, now let's come to the importance sampling. Using the very same idea, if my P is very difficult to sample from, just club it with F, find something else which is easy to sample from. Sorry about my voice. I want to compute E of F, which I know is equal to some F of X times P of X dx integration. But what I will do is, I will club these two. Basically, this thing would have been equal to fx s summation over all the s and 1 upon capital S, where xs is
sampled from P of X, right? So what I do now here is, I will say this is equal to summation f of x, P of x divided by some Q of x multiplied by some Q of x dx. And this whole thing, I say this is equal to 1 upon capital S summation over the samples. Now this whole thing becomes my function, f of xs times P of xs upon Q of x. And where my xs now is sampled from where? From this Q of x. Which is easy to sample from, right? Does that make sense? Does that make sense? Okay. So now what do we see here? We see that the formula was exactly same, but this extra term has come. So we call this term as this whole thing. This thing is called as, these are the importance weights. This is the importance weight. And what is this equal to? This is simply P upon Q. So essentially, if your Q is exactly same as P, then this is always 1. But if your Q is something different, then sometimes it will be smaller than 1, sometimes it will be larger than 1, so that overall it will be balanced out over the summation. So this concept is called importance sampling. Right? So let's say you had a, let's take an example here. You had a complicated distribution. Right? This is my P of X. You take a simple distribution, maybe a Gaussian distribution. This is my Q of X. Right? Now what do? I sample from Q, and then I have some function f. I multiply that function with P upon Q. Sometimes it is larger than 1, sometimes smaller than 1, because the area under both the curves is 1, right? So sometimes this will be bulging out, sometimes it will be compressed or going in. And in this way, using these weights, you can compute the expected value. Is that clear? It's a very simple concept. Let's now see when there can be a problem. Let's consider a situation. So means this has also got its own limitations. So here we took 2 PDFs which were approximately same, more or less same. But what if we have a PDF like this? My P of X is, let's say, something here. Here it is very small. And my Q of X is something here. Here it's very small. Right? This is my Q of X. And this is my P of X. In this case, my importance weights will be mostly very small because my P upon Q is very small, right? So here in this region, my weights are small, right? What is my weight? This P upon Q. So my P upon Q is, let me use some shortcut notations. P upon Q is very, very small, right? And most of my samples come from here, right? Most of my samples are coming from this region. And here my P upon Q is very, very small. And I have very less number of X coming from here. Here P upon Q is very, very large and very less X come from here. Very less number of samples are coming from here. So if I'm doing, because to do Monte Carlo, I'll be just using some finite number of samples, right? And let's say if in those finite number of samples, this area is not well represented, then again, my estimates will be very far from original or far from the actual, right? So that's what we don't want to happen. We want our P and Q to be approximately same, so that, so this is the thing. So my Q of X should be significant wherever P of X is significant. Means it shouldn't be too far. It could be something like this. Spoil this figure. Okay, let's use some other color. I can have my QOX something like this. That is still acceptable, but which means it has significant portion here. But okay, there are some here which will not pay much, which won't have any importance. These ones which have importance, so QX should be significant here as well. Right? This is better QX. And this one is a bad QX. Right? So that's the thing. QX should be significant wherever PX is significant. This is all about importance sampling. So basically we are reducing these importance weights while sampling from a different distribution. Okay, very powerful concept. Now, what happens when, just a peripheral discussion, what happens that when instead of Px, I have got P tilde X on some normalization constant. So what I can do is I can also choose a QX of similar form. Let's say this is Q tilde X upon some Z. Now these Z's may not be same. So let me call it as ZP and call this as ZQ. There will be different normalization constants, right? Because anyways, we are not computing normalization constants, so they are different. Now what we can do is in estimating E of F, I'll be saying this is basically F times P, Fx times Px. I don't know Px, I know P tilde upon Zp. And I will be multiplying it with some Qx dx. I'll be dividing it with some Q tilde X on ZQ. Right. And then integrating, and this whole term, this whole thing becomes my importance, or sorry, my term which appears in the Monte Carlo sampling, F of XS. I can say here P tilde of XS upon Q tilde of XS times, okay, no times, summation over S equal to 1 to capital S. And here we have 1 upon S, and this term ZQ upon ZP. This term appears. So everything is easy. Sampling from QX is possible. Computing P tilde and Q tilde are possible, but computing these terms is very difficult. So what do? So we can again use the similar form. Some formatting. Okay, we can use similar form to estimate ZP upon ZQ. So what is ZP? What is ZP? Yes. ZP is the integration of Px dx, right?
P tilde.
No, oh yeah, yes, thank you. Yes, integration of P tilde x dx, thank you. And what is my Qx? Qx is integration of Q tilde, but instead of writing that, I will write, so I know my Q is Q tilde upon Z. Right? So I'll use this form. So this is basically Q tilde x. Let me write it inside the integration. Right? Now this thing can be written as P tilde x upon Q tilde x, right? And Qx will go up. Now what do you get from here? What do you get from here? This part is something important, right? This means I can use Monte Carlo again. You can use any PDF, combine it with the integration and use Monte Carlo. That's the basic funda. So you have P tilde x on, sorry, xs. I hope it's clear. Q tilde x. And my samples are going from 1 to capital S. Does that make sense? So I can use the same samples. These x tilde, sorry, these xs are coming from again qx. And they can be the same samples what we had earlier. Oh, here I didn't write. My xs are sampled from qx. Right. So let's now combine both of these. So what do we get? So this thing is equal to, now I have to invert this thing and this will become basically 1 upon n, 1 upon s, 1 upon s get cancelled. Let us call P tilde upon Q tilde as R tilde, ratio or importance weight. R tilde s, where R tilde s is simply P tilde of xs upon Q tilde of x. Right, then let's put it back in this equation. We get my expected value of f is equal to what? 1 upon s, something r tilde, 1 upon s gets cancelled. This is basically summation over s equal to 1 to capital S, r tilde s times f of xs upon summation s equal to 1 to capital S. That's it. And where my xs is sampled from qx. So in this way, when you don't have the value of normalization constant, then also you can use importance sampling. Okay, I think that's pretty much it. Do you have any questions? No questions? Let me zoom out and show you what we did today. We started from a simple concept that that our PDF is like uniform sampling in this region, in this this joint PDF kind of region. And then we went on to use this concept for rejection sampling, where we rejected the things which lied outside this region. And then we discussed importance sampling, which did not reject anything, but rather used an importance weight to give different weights for different things. Things which are very far from actual, they get less weight, and things which are close to actual, they get more weight. So in this way, we discussed. Any questions?